it's nice, then I think the lineup of organizers is doing better. I hope I speak for speakers. So, thank you for having me here. I was thinking a lot about what to say about this topic. First, I thought that I have basically nothing to say because, well, I'm working on AGI. What do I have to say about representations? Then when thinking a little bit more about it, I figured that actually throughout my career I have been working a lot with representations. So I figured I'll just give you some kind of idea of where I'm coming from. Like why do I think the way I do? So that's the title. I'm going to argue that in order to have good representations, and now for decision-making agents, you need to look at relevance, inference, and statistical structure. And those are the principles. I'm trying to give you some examples of how that works. But before going there, my career, how did I end up here? In 1990, I was 17 years old, and I was planning to go into biochemistry or something, genetics. But then I read this article about neural networks. Pioneer in the field, Teuvo Kohonen, had written this stuff, and I completely fell in love with this stuff. Brains, neural networks, this is the future. So 3 years later, I was his research assistant, working on learning representations of speech data with self-organizing maps. So those of you who are too young to remember, Kohonen maps are one of the early unsupervised learning algorithms that imitate the way the brain self-organizes. The cortical representations self-organize, and that's it. I was his research assistant working also on learning representations of image data with slow feature analysis. It wasn't called like that at the time, but that's what I was doing. And then I figured, well, the brain is using sparse coding, so I made my master's thesis about learning representations of image data with sparse coding. Less than a month after I had submitted my master's thesis, Olshausen and Fields published their sparse coding paper in Nature. So I was completely overrun by the gurus, but I still thought that there's a lot of interesting stuff to do in there. I figured I want to do non-linear versions because all of these things were linear. So then I ended up doing variational learning for non-linear latent variable models. So basically very similar to what people would call variational autoencoders these days. First, it wasn't an autoencoder, just a latent variable model. But at that time, independent component analysis, nowadays it would be known as disentangling factors of variation, or what's the term? So basically the same thing, but nonlinear versions of it. And in some sense, it was a self-caused problem that I had to use these fancy Bayesian things because the models are so flexible and complex and so on that they completely overfit to the data unless you do proper inference, and that's why I ended up in this stuff. I actually sort of invented variational learning, tried to publish it, but then the reviewer said that this has been invented already, and again, completely overrun by the gurus. I was working also on applying this stuff for state-based models, so recurrent neural networks, temporal data and stuff. Interesting stuff. But not the final truth, I thought. I moved to hierarchical latent variable models because, there is a hierarchy of representations in the brain, and I figured that would be something. So 10 years of unsupervised learning. What the hell is the use of that, all of that? So I wanted to really understand, why do we do all of this stuff? And thus I went to, oh sorry, I'm jumping ahead of stuff. So still one thing, these methods were very complex, Bayesian inference and message passing in latent variable models and stuff like that. So inference was always an issue. So in 2001, I worked on amortizing the posterior inference part with MLP networks. So that's an early example of variational autoencoder, not the way it's done these days, mind you. So I had slightly different stuff. I was iterating after this, like MLP network gives an initialization and then iterate stuff. Then I looked deeper in this because it was bothering me that we are doing all this fancy modeling, but the end result is often very simple. So if you do all the Bayesian stuff, you end up with fairly simple inference algorithms in the end, this message passing. And that started bugging me. Very complicated things and also limiting things, because we are limited in what we could model and solve mathematically. So I started looking deeper into this inference thing. And that led me to something I call denoising source separation. So basically replacing the E step, which is about, doing Bayesian analysis, computing posteriors, and so on. Just throw in the algorithm, which is basically doing this denoising step. What the prior is usually doing, you can see it as denoising. You have some observations, and then what your likelihood is saying is like noisy raw stuff, and then you put your prior in, and this prior kind of denoises this solution. So why do we do all this complicated stuff when we can use very simple procedures for denoising? Like median filtering, for instance. It's very difficult to express exactly what leads to median filtering, but the end result, the inference part, is really simple. So then I started looking at why are we doing all of this stuff. I went to robotics. So in Zurich, doing postdoc in developmental robotics project, ADAPT. These European Union projects, if somebody knows about them, they are often very forward-looking, and so we were developing a 2-year-old child robot, and there were many people working multiple aspects like hands and so on. My part was building the brain for this 2-year-old. That was interesting, but I have to say we went completely successful, so it's not quite 2-year-old baby, but this was cool stuff. But that really made me think, are we actually solving the right problem at all? Like all this fancy unsupervised learning and so on. What the hell is the meaning? Like very complicated stuff, but not all of it works in the real world. So I've always been very interested in the brain. I started my own research group, computational neuroscience, on neurorobotics. So basically what we were doing was building a bio-inspired cognitive architecture, which has cortical model and for learning and segmentation and all of that stuff, and basal ganglia model for reinforcement learning, and cerebellar model for fast control. So I had to look at how the brain actually does things, because it's not doing variational Bayesian learning and all of that stuff. It's just doing a lot of useful stuff. Started a robotics company, so really wanted to apply this in the real world. So we ended up doing weight sorting with robots. There was recognition and segmentation. My part was model-based reinforcement learning for picking. So this is how these babies look like. This is from 2012, I think. So pretty cool stuff. Unfortunately, we weren't able to publish anything, so nobody really knows anything about this stuff. But that's reinforcement learning in the real world. Okay. Oh, by the way, usually in robotics, people show faster than normal movies because otherwise it looks dumb. In Zen Robotics, I'm happy to say that these were even cooler when showed in slow motion. So I think that's one Turing test for robotics. Okay, so having done all this, the next step, artificial general intelligence. That's what I've been doing for the past years. So after having solved all the problems in waste sorting, I founded another company, the Curious.ai company. What we are doing is tackling the problems which are most important for solving this AGI. Artificial intelligence with internal simulations. So much like AlphaZero. You all know AlphaZero, right? It has this very, very nice internal simulation of the game, and then it learns to amortize this inference, and it's a nice loop going both ways. But it doesn't learn the rules of the game. So what we are doing is working on something like that, model-based reinforcement learning, where you actually learn the rules of the game. Learning is made more efficient by semi-supervised learning, online learning, and now we are getting to the topic of today. Also, one of the key missing components, I think, is neurosymbolic networks. Our neural networks are not really able to properly represent interactions with objects and so on. They can't even properly represent the objects, I think. Marta is going to talk about that stuff in the last talk, so stay here for the good parts. Anyway, so now a very long introduction to where my thinking is coming from. I'm trying to build AGI, so systems that learn, behave, make decisions. I'm not working on image compression, for instance, so what I'm going to say doesn't apply everywhere, but I think it does apply for intelligent learning systems. So as I said, semi-supervised learning is one important part which we've been working on. I'm just going to show you the recipe that I have for semi-supervised learning and try to explain why. So first of all, I think there always needs to be a primary inference task. Otherwise, all this representation learning is completely useless. Like, why? Why would we learn anything, any representations, unless we want to use it for something? So I want to have always a primary task. And not just any task, but a task which requires inference. So for me, representations are the things that lie between data and the final decisions. Anything in between is representations, in some sense. This inference task could be classification. So that's certainly an inference task. Implicitly, I think these deep neural networks, they're doing a lot of inference inside. So you can often dig into the representations and see that there are some intermediate values calculated by the system, and you can interpret them as representing some latent variables, for instance. That's, to some extent, that's in the eye of the beholder, I think. They need to do this stuff, and our brains, these deep neural networks, they're just calculating stuff. And of course, while doing that, they have to solve this inference. And if you look at any inference algorithm, there are some representations. So I can't maybe explain it properly, but to me, there is no reason for doing explicit latent variable modeling or something like that, because the thing that we are really interested in the end is the inference. So classification is an easy task. We have been using it as an example case for basically all our publications and so on, but what we are really interested in is prediction of value and optimal actions. So if you read our papers, you can switch classification with this task and everything works as before. Then that would have been just supervised learning. But now we are using these auxiliary inference tasks for helping the primary inference task. And again, there can be many. So it could be classification. Then you have transfer learning or something like that. It could be prediction. We have been working on that stuff too. And denoising. So if you know my famous ladder network paper, that was using denoising. Just one example of an auxiliary inference task that you can use. So, as I said, I think I'm known by deep learning people as the ladder network guy, because I gave a talk in NIPS 2015 about this stuff. My thinking behind it is that actually I have some kind of static hierarchical latent variable model, and then I'm thinking about all the message parsing and inference that you do in that. And then look at just the first pass, bottom up and top down pass of message passing, and see what is the computational structure of that. And then just take the computational structure and give this network a task, like denoising, which makes it necessary to do that inference. And then, if you do it well, and you are lucky enough, this secondary inference task will help the primary inference task, which is classification or prediction of value or whatever. It will help that primary inference task. And we got state-of-the-art results in MNIST and stuff, so cool. But obviously this is not why we were doing all of these things. And so the ladder network is just the simplest possible version of this principle, that you take some kind of inference, and then you think of some latent variable models or some representation like that. You take the inference, and then you just model the inference directly without going into the gritty-nitty details of, okay, is this latent variable model, is it directed graph, or is it energy-based, or what? I don't care. This inference will look the same no matter what. So that's, from my past, this is a lesson that I learned. If we do explicit modeling, we are often restricting ourselves too much. So the networks that we are using could do much more than what we are allowing the explicit model to do. So, extensions. By the way, how am I doing with respect to the time? I still have a few things to say. When was I supposed to end this babbling?
We are going through like 1 and 20 minutes.
Oh, good. You're going to hear more about our later work. So, simpler extensions of this. What if you had more complicated latent variable model, not just a static hierarchical latent variable model? So, for instance, what if you have temporal sequence? So you have hierarchical temporal latent variable model. Then our recurrent ladder network can do that kind of stuff. Then what about if you have models which have, say, multiple objects and like, for instance, in parsing images, for instance. Then you need, in practice, you need to have iterative inference in these kinds of things. Just one bottom-up, top-down pass won't be enough. So you would like to do multiple passes and you get into iterative inference. There are many interesting problems where you really have to iterate in order to get a solution. So this is what we were working on, publishing in NIPS 2016. So I'm going to show you these examples. I hope it will still further clarify what I'm thinking. So let's take this kind of toy problem, occluded moving MNIST. There are 5 different examples of the data. The primary task here, let's say that is classification. We want to classify what this digit is. And suppose it's a semi-supervised setting, so we have a lot of data, but we have only some labels. So if the primary task is classification, it's easy to see that if we take as the auxiliary task prediction of the next frame, then much of the same inference that you need for classification will be there. So in order to better understand what this data is, it has these bars, but they are not shown. These bars are not shown for the network. So it has to infer all of that stuff. So if you think of what does the optimal inference look like here for recognition, first, when you have this long sequence, the optimal stuff to do is try to reconstruct what these pixels are. So when it's moving, you can keep track of the pixels that you didn't see. So you estimate the velocity, then you use that velocity estimate to align the different frames, and then you sort of fill in the pixels. So here's an example. If you have observed frames on top, then the reconstruction is on the bottom. So you just keep track of these digits. Then once you have that stuff done, and you can feed back information about what the digit might be in velocity estimates and so on, but that's a minor detail. Let's skip that. Then in the end you have some observable pixels, and you need to estimate that. So this is an example now of a toy problem where we have it's easy to see how the low-level task prediction could support this high-level task. Of course, we are interested in more complicated stuff, like you take actual videos and so on. So a recurrent ladder network, like what are the inferences you would need to take? First, you would need to estimate the velocities. So you have some kind of computations there. Then once you have those estimated velocities, you need to keep track of the observed pixels by shifting the previously recorded pixels, and then in the end you do classification. So when we tested this, and we wanted to see if this actually does it work like predicted. So the bottom line here, you get less than 1% error, like 0.9 approximately, if we cheat and we do the optimal reconstruction. So we take the golden standard, we sort of put in knowledge about the velocity, and we just reconstruct the pixels, and then we see how a static network could work from there. And if we just take a temporal baseline, so you know this, you have a convolutional network, and then you have some LSTMs on top or something, you don't get nearly as good performance. If we use hierarchical structure, recurrent network, you get slightly better, and if you add this top-down, bottom-up thing, you get even slightly better. But still, here we didn't have a secondary task, so the improvements are not so good, not so amazing. So just having the right structure isn't enough, obviously. But when we add the prediction task, then it makes a drastic difference. So now we also try to predict on top of just trying to classify, and we get basically very close to optimal. So optimal in the sense that very close to the golden standard example. So it shows that just doing prediction forward, coupled with this primary task, helps us find the right inferences. One thing that I wanted to point out is that people often think of this Bayesian golden standard thing as probabilistic. Like inference is probabilistic. What does it mean? I would say that inference is deterministic. The computations are deterministic, but you represent uncertainties. And in this case, for instance, we can clearly see that this network also manages to represent uncertainty. Yesterday, Zubin was saying that deep learning is pretty bad at representing uncertainty, but if you give it the right tasks, it's really, really good at learning to represent uncertainty. And here's an example. So you have, on top you have the observed sequence. So in reality it's digit 3 moving, but you only get glimpses of it. So when we look at what the system is predicting as the next frame, you can see that after seeing the first frame, it has very blurry prediction because it still doesn't know what the velocity is going to be. It has learned some kind of implicitly learned a prior over velocities, and then it's integrating over that. Once it sees the next frame, it gets spot on. Okay, so this is how it's moving. So the next prediction will be very sharp. So all the uncertainty disappeared in one frame. It still is. It's actually thinking that it's different different digit. When we are probing the network, we are trying to make a prediction of what the unmasked digit is. This is not part of learning, but we are just probing this network. We can see that it's kind of thinking that it might be a 5, and you can also see it in the prediction of next frames. So in here, there is this tiny little pixel that you see that the network predicts that it's probably going to be 5. It's not quite certain, but it thinks that it's going to be 5, and maybe this pixel is going to appear. It failed to appear here, so just one pixel failed to appear, and snap, the network changes its mind. Okay, maybe it wasn't a 5, maybe it's a 3 after all. So when we do probing, it looks like 5, and then looks like 3. So I've been really astonished at how good Bayesian analysis these kinds of networks can do. It's kind of unfair, having done a lot of Bayesian latent variable model stuff and doing the maths the hard way. It's kind of unfair to see a neural network just do all of that stuff like that. So, I still have like 10 minutes, right?
Yeah, you might want to leave a bit of...
Yeah, okay, so I'll rush. So that was inference implicitly inference in a latent variable model which has already pretty complicated structure but doesn't really talk about multiple objects and so on. But if you look at the real world, we need to tackle that problem. Like this is something I think Marta will agree with me, and will explain in the last talk how to really do it. But understanding objects and being able to represent those is really, really important. All the relations and symbolic knowledge and all of that stuff. So how do we do that? Can we get neural networks to imitate the kind of inference that you need to do if you want to solve problems where the latent variable model implicitly talks about multiple objects? So in some sense, lists of objects. It's not easy necessarily to represent that kind of stuff with standard neural networks. But what we developed is very, very similar principles as you just saw, but now implicitly in a more complicated latent variable model. So the idea is that if we want to represent an image as a set of multiple objects, which are then overlapping and so on, we can do it in semantically this way. So there are multiple individual objects in their different slots, and each one has their own mask somehow, and the occlusion mask. Like which pixels are we actually seeing from the objects? It's a very complicated inference process if you think of building a latent variable model and doing that. People have done that actually, and you can iterate, and it takes quite a bit of time. So what we started with is think of these kind of latent variable models and think, what are they doing? So if we now take, again, a denoising task, which is, so this is, on the left you have a sample noisy image, and on the right you have the ground truth clean image, and then in between there is stuff which figures out that, hey, actually there's some kind of grading as a background. So this kind of background, and the black pixels here denote the ones that are visible, and then some other gradings. And then we just learn this in completely unsupervised manner. We throw in these images and let the system learn the inference process, how you get from this noisy image to the end result on denoising. And you have to go through splitting this image into different parts, because that's just optimal inference in this case. And looking at the latent variable models, if you have multiple, in this case, the underlying assumption is multiple independent objects, then you do a lot of inference about these independent objects, and then you combine them, and then you iterate. So it's definitely iterative thing, and we just take that network structure and train it to denoise, and voila, it gives us an algorithm which completely beats humans even in this task. Humans are supposed to be really good at perceptual grouping. It also beats in speed, how fast it can converge in these iterations. It beats any of these handcrafted latent variable models plus Bayesian inference. And then we can do plenty of stuff with that. Okay, so we published that in NIPS 2000, and also works for temporal sequences and stuff. So the last thing, sorry, I'm going to use basically all of my time. There's a problem here, and this is what I really bumped into when going to robotics. All of this stuff works so nice in simple toy problem settings, but then you take real world, like garbage sorting robots and so on, and it completely breaks down because there's so much irrelevant structure. So it's a nice story that you just take some auxiliary tasks which share a lot of the inference, but if you try to apply that principle in the real world, it's not so trivial. So let me give an example. We try ladder network for this kind of MNIST classification. It works very well there, but then we put CIFAR 10 backgrounds just to fool the network, just to mess up with it a little bit. So 1,000 labeled images, an additional 49,000 unlabeled images. Sorry, this is a slightly small figure on titles. Labels are small, but on top you see that the ladder network without any background gives like a little bit more than 1% error in this case. If you just take the encoder, you get like 4-point-some% error. So this additional inference task of denoising, if you don't have background, really helps. But when you add the background, the gap between, like how much you benefit from denoising, it really drops drastically. So all the results drop. Just the encoder drops to 7%, more than 7% error, and now denoising doesn't help so much, so you get like 5% error. So how to fix this? This is not just a problem here, but it's always a problem when you have primary tasks and then you have some auxiliary tasks. What to do? So our solution is to add kind of attention to learning. If you think of just the encoder, so here we have a noisy version of a 9, and then there's some background, and then we train an encoder. We can use the gradients to see what does the network pay attention to. And then we can use that gradient to modulate. So this is the normal ladder network with a denoising task on top of that classification task. If we modulate this cost function with this squared gradient. The squared gradient is, you can see it as an approximation of the Fisher information and so on. It tells you which kind of metrics you should be using. If you take the full Fisher information matrix, it's kind of computationally demanding, but we just take the diagonal. When you do that, you can use your primary task to tell all the auxiliary tasks what is it that they should be paying attention to. And then we get really, really nice results. So these were the results without background, and these two here were the results with background. And now when we add the modulation, we get results which are almost as good as without background. So this really, really helps. Okay. So this is now the summary. You start. So this is my recipe for semi-supervised learning and how to really properly learn representations. You start with the primary inference task. Could be classification, could be, in our case, we are mostly interested in prediction of value and optimal actions. Then you add some auxiliary tasks. You can have many types, classification, prediction, denoising, whatnot. But then you use the primary task to select the relevant parts of the auxiliary tasks, and then you are golden. So, to repeat, I think optimal inference is deterministic, but when you model, when you do this inference, it has to talk about uncertainties and all of that stuff. So I think the very good use for neural networks and so on is to model the inference rather than this probabilistic whatnot. It will find representations. They can be redundant, they can be all kinds of different things which are not good for compression, for instance, but they are really good for making the inference work properly. And disentanglement is something which I would claim is necessary, because that will make it possible to modulate different tasks or different parts of the auxiliary task separately. So some of the things are irrelevant, some of them are relevant, and it's highly likely that the boundary between relevance and irrelevance is sharp if you do disentanglement. That's it. Thank you.